In this video, we'll talk about the method called variation of parameters for solving non-homogeneous equations. So the benefit of this method here is that it works in much more generality than undetermined coefficients. It's a formula that works all the time and sort of gives the theoretical result of these solutions always exist because I have an implicit formula for them, just like we had for first-order linear equations. The issue here, though, is these formulas are given in terms of integrals, and it's not always possible to evaluate these into closed form expressions. We might not be able to actually write out the equations from them. We can have a method that will always give us the solution if we can work out the integrals. The idea of the method is as follows. If I have my equation that's second order linear just like this, and assume that I know the functions y1 and y2 that solve the homogeneous version of this problem. So if I know that, because this equation is linear, we then know that any linear combination of y1 and y2 also solve the homogeneous problem. That means that our general solution to the homogeneous problem will be a c1 times y1 of t plus c2 y2 of t. This also solves the homogeneous problem. So the idea of variation of parameters says I know this solves the homogeneous problem. So what I'm going to do is I'm going to take this c1 and c2 and make them functions of t, and hopefully use this combination here to then solve the non-homogeneous problem. By making these functions of t, they no longer solve the homogeneous problem. So we'll be able to pick those functions to then make it solve the non-homogeneous problem. The goal, try yp of t, this one particular solution, as a function u1 of t times y1 plus u2 of t times y2, and figure out what u1 and u2 are supposed to be to make this solve the non-homogeneous problem. The idea here is similar to that for reduction of order. The idea being the fact that I know that y1 and y2 both solve the homogeneous problem might mean that when I plug this in to try to make it solve the non-homogeneous problem, parts are going to drop out because the y1 and y2 terms are going to go to 0. And we'll see what that happens as we work out the algebra here. So here's the idea here again typed out. We have our equation. We know that our general solution for the homogeneous equation, where I drop the g of t, is c1y1 plus c2y2. I'm going to plug in y as u1y1 plus u2y2 and see what happens. Let's start by taking derivatives of this y before we go ahead to plug it in. So we can take the first derivative, and we'll get product rule on both terms. And I'm going to regroup these terms slightly. And before we go on, we're going to make a simplifying assumption. So we're going to end up with two equations here involving our unknown functions u1 and u2. That's going to be our end goal. But we only start with one equation up here. So we're basically allowed to pick another one to make our lives easier. And the one we're going to pick is we're going to pick the equation that makes this term here equal to 0. So we're going to pick this and make this happen as our second equation for this method. So we're choosing to make this happen. In general, you don't have to do this, but for this method, we're always going to make that assumption there for this problem. That means now we can take the second derivative, and we're going to have a lot less terms in the answer because we've gotten rid of that equation over there. Now for a second derivative, we're going to get y double prime, and we're only going to have 4 terms because these are the only 2 that survive in the first derivative. And now we're going to plug everything in and try to make this solve the non-homogeneous problem. So we're going to end up plugging this all in to y double prime plus p of t times y prime plus q of t times y, and I will set this equal to g of t. So I can plug in my derivatives and the functions into these spots here. And then we want to rearrange this equation based on the u function attached to each set of terms. So we'll do that here and see what we get. The main point here is not all this algebra. Algebra is kind of the tedious part to get there. We'll get to an actual formula in a minute, which is how you actually solve out these equations. But let's first group this stuff by the u coefficient of each term. So I see a u1 prime from the first term way up here, and that's just multiplied by that 1y1 prime. It shows up nowhere else in the expression. I see a u2 prime here on this third term. That is also just multiplied by y2 prime. And then I have other stuff. So I see u1, and that's multiplied by a y1 double prime up here, a p of t times y1 prime here, and a q of t y1 down here. And in the same way, we see for u2 that it is multiplied by y2 double prime plus a p of t y2 prime plus a q of t times y2, and this must equal g of t. And here's where the benefit comes in. Just like reduction of order, you do this the right way, and we notice that these two terms here both go to 0 because y1 and y2 solve the homogeneous problem, which leaves us with an equation that looks not too bad. It is u1 prime times y1 prime plus u2 prime times y2 prime equals g of t. And then we can pull down the equation we had before as our extra condition that we imposed. I'll do it in green because it'll match the green that it was before. u1 prime times y1 plus u2 prime times y2 equals 0. This now gives us two equations for the two unknown functions u1 prime and u2 prime, which is really good. It means we have an opportunity to try to solve these out for u1 prime and u2 prime, and then integrate to get u1, u2, and backtrack to our original particular solution we were looking for in the first place. So now for more messy algebra, let's solve this out. So we had u1 prime y1 prime plus u2 prime y2 prime was g of t, and u1 prime y1 plus u2 prime y2 was 0. To solve out, I'm going to multiply this first equation by a y1, the second equation by a y1 prime, and then subtract them to give me the fact that the first terms cancel out, because this will be a u1 prime, y1 prime, y1, minus u1 prime, y1, y1 prime. Those will cancel out. And I will end up with a u2 prime, y2 prime, y1, minus a u2 prime, y2, y1 prime, equals g of t times y1. I can then factor out a u2 prime here. u2 prime times y1 times y2 prime minus y2 times y1 prime equals g of t times y1. And then I can solve it for u2 prime. u2 prime will just be g of t y1 divided by y1 y2 prime minus y1 prime times y2. And that's the answer. Why do we know this works? Well, I divided by something. I better make sure that's not 0. But we've seen this expression before. This is the Wronskian of the two solutions, and we know it's non-zero because we had a fundamental set of solutions, or a general solution, when we started the problem. So I'm okay with dividing by this term because I know it's never going to be 0. So that gives us u2 prime. I can then find u1 prime by plugging this back into the second equation here, and that's going to give me that u1 prime is negative g of t times y2 over the same expression. Basically taking a minus sign, multiplying by y2 and dividing by y1 to solve for u1 prime in that first equation. And then I can integrate both of these, or anti-differentiate them, and then write out my full answer, because my solution, remember our whole start for this process was that our yp of t was going to be u1 y1 plus u2 y2. So if I can integrate these two functions explicitly, I can find their antiderivatives, I can multiply them by y1, and we're good to go from there. In terms of integrals and sort of written out formula, it would look something like this. Our yp of t is going to be u1. I'll put the y1 of t in the front. And then u1 is the integral of that expression there. So a negative sign, integral from some convenient t0 up to t, g of s, y2 of s, over this Wronskian expression of s. The s, and right, and the s here is a dummy variable. It's just saying integrate this to get this into a function of t that you get at the end. And then that's the u1 term. And then the u2 term looks similar, plus a y2 of t, integral from t0 up to t again, g of s, y1 of s, over that same term again. So that solves out for the particular solution, and that's the formula that you just use for doing variation of parameters. But then remember, you're not quite done yet. Your general solution y of t is this yp from above in that box, which could be really long and nasty, and then plus the c1 y1 of t plus c2 y2 of t that we know solves the homogeneous problem. That feels like a lot of long-winded calculations and a lot of just stuff happening there, but the main point is this is an explicit formula that works in every case, no matter what g, y1, y2 are, as long as they are a fundamental set of solutions, y1 or y2. This works every time. And that's the benefit of this method, is that no matter what you have for anything, this works. You might not be able to actually write out these solutions to the integrals because they're too long and too complicated and they're not closed form expressions, but it's an expression that works and sort of proves in some sense that these solutions always exist because I have a formula I can write out for them and for how they work. That's really the main point of variation of parameters. It works every time, and you can use it to find solutions in certain cases when you couldn't otherwise.